Hello everyone, I'm Hao Wu, a PhD student from Huazhong University of Science and Technology. Today I'm glad to share our work, StreamBox, a lightweight GPU sandbox for serverless inference workflow. This is a joint work with Yue, Junxiao, Deng, and Shadi from Inria. So, in recent years, inference service has been widely used in various fields, such as surveillance, auto driving, and video processing. Inference service is usually a workflow composed of multiple DN models. For example, a traffic monitor application consists of an object detection model and two recognition models. Deploying inference service on serverless platforms have become a trend. Serverless inference offers many benefits, such as no need for GPU cluster management and the efficient GPU utilization through the fine-grained allocation and auto-scaling. Inference service typically do not need a full GPU. Given the small batch size and varied parallelism, we need to share GPU properly. There are different types of GPU sharing, such as temporal sharing and spatial sharing. As shown in the table and figures, existing serverless inference systems run concurrent functions in isolated GPU runtimes, regardless of the type of GPU sharing. However, the default GPU runtime is too heavy for short-lived and fine-grained functions. We take the state-of-the-art serverless inference service, Inflex, as an example, and analyze the three limitations of the default GPU runtimes. First, high memory redundancy. We test the memory footprints of GPU functions for different memory machine learning frameworks and models. As we can see, the total memory footprints of a function can be up to 1.5 GB, with 90% occupied by the GPU runtime, like GPU context and the libraries from the machine learning framework. We can see that the blue part in the figure on the left. Actually, the GPU runtime can be shared among functions in an application, as the developed setting of an application is usually the same. Therefore, initializing separate GPU runtimes leading to significant data redundancy and then limited deployment density. As shown in the next figure, a V by GPU with 16 GB memory can accommodate up to 8 functions, but over 60% of the computing resource remain idle. A second one is the cold start overhead. A GPU function takes 5 to 6 seconds to complete cold start, mainly due to the GPU runtime initialization, like setting up the GPU context and importing libraries. Other parts, such as model loading, are only 100 milliseconds. And the warming up functions is a common method to reduce cold start, but the GPU runtime's memory consumption we mentioned above results in only a small amount of functions could be warmed up in the GPU. So, as shown in the figure in the right side, even if we apply the warm-up optimization on existing serverless inference system, the impact of cold start is still significant. And third one is the communication overhead. Each GPU runtime has isolated address space, so data transfer between the functions must pass through the host memory, involving like back and forth data copies between the host memory and the GPU memory. While modern GPUs provide an ATC method for sharing GPU data directly between the process. This introduces additional overhead. Ideally, when two functions are on the same GPU, the intermediate data should be shared and accessed directly. So, as shown above, default GPU runtime are efficient for serverless inference. We argue that functions of the same inference application do not need such strong isolation, especially identical functions that scaled up when the workload increases. Modern GPUs offer GPU strings in the GPU runtime, similarly to the thread in the process. We use a GPU string to run concurrent functions in the same GPU runtime. Strings offer several benefits. First, the fastest startup and low memory footprint. There's no need to initialize or separate GPU runtime for each function. And the second, faster resource reallocation. GPU resource partition across strings can be done in software level method without reinitializing the GPU runtime as required by the NVIDIA MPS. And the third one is efficient resource sharing, because strings share the same address space, allowing more easily memory sharing between functions, which improves the GPU memory utilization and facilitates the zero copy data transfer between functions. Despite the potential gains of using strings, GPU strings for serverless functions still face several challenges. The first one is the function, when functions running on GPU strings and allocate memory within the same address space, which will require proper memory management. Because concurrent memory management is coarse-grained, leading to delays and unnecessary GPU memory restoration. For example, existing memory management systems like PyTorch establish a static memory pool to cache released memory, which can lead to excessive memory usage when running multiple functions in a shared memory space. And second one is, although functions on the same GPU can achieve zero copy data transfer through strings, the placement or like the distribution of the function depending on the load balancing and is dynamic. For instance, functions in an application may be distributed across different GPU and different nodes. Therefore, a seamless communication framework is so challenging. Furthermore, when we catch the intermediate data inside the GPU memory, we need an effective management of this intermediate data just to avoid memory contention. And the third one is due to each GPU runtime in GPU driver has only one I/O engine. So the data strings can only use PCIe bandwidth in an exclusive manner. As a result, the first arriving data strings will monopolize the bandwidth until all data transfer are complete, which hurts the parallelism of the function running on the strings. So this slide shows the architecture of StreamBox. In the online phase, StreamBox hooks various GPU API from functions and forwards to them to API proxies. An API proxy is responsible for an application. The API proxy allocates a string to execute a function's API. In the offline phase, StreamBox will recompile the Deng model's kernel so that it could support GPU partitioning at the software layer. The recompiled model is stored in the model pool for reuse. Furthermore, the challenges of applying strings motivate three components in StreamBox. The first one is StreamBox builds an auto-scaling memory pool to improve memory efficiency. Our key idea is to combine the layer structure of Deng, allocate memory on demand and layer by layer, and reclaim the space in time. This fine-grained memory management can improve the efficiency of the shared GPU address space. And moreover, considering the computation of the pre-trained model is fixed, we provide the memory usage of each function offline, and we can finely control the size of the shared address space according to the profile data during the runtime to reduce the memory waste. And the second one, StreamBox provides a transparent communication interface for developers to compose their function workflow. The unified communication framework can adaptively switch the communication method between the functions based on the distribution of functions in the GPU cluster. In addition, StreamBox also adopts elastic communication storage, which can effectively use ideal GPU memory to store the intermediate data. When the memory pressure of the GPU increasing, it will adaptively move the data to other GPUs or the host memory. And the third one is to enable PCIe bandwidth sharing among concurrent streams. StreamBox partitions the data of functions into smaller data blocks and use the I/O daemon to globally schedule the transfer of these data blocks. And we choose the optimal data block size and use like pin memory buffer to improve the utilization of the PCIe bandwidth. In addition, when we split the data into chunks or data blocks, the original synchronization between the kernel and the data copies in the user code is failed, so requiring us to rebuild the synchronization. So next, we conduct an intensive comparative experiment. Our experiments are conducted on a server equipped with 4 V100 GPU and use real-world trace to simulate the workload. In addition to comparing existing serverless inference system, we designed a string-only baseline. That is, we remove our 3 optimization based on our approach. I will show the key results here. We can observe that StreamBox significantly reduced GPU memory usage compared to all baselines. Furthermore, StreamBox reduced memory footprint by 71% compared to string-only because of the fine-grained memory management. StreamBox allocates exactly the memory needed during the Deng inference computing through the lazy allocation and eager recycling. We also observed that the StreamBox achieves the highest system throughput as the warm-up method is ineffective on the GPU. Existing serverless inference systems are still affected by the cold starts, which cause a lot of request timeouts. But StreamBox outperformed the string-only due to the more efficient memory management. So the allocation overhead of the memory is lower, and the communication is more efficiently. And we can also see the StreamBox achieves the lowest latency and SLO violate rate. Frequent cold start in existing serverless inference system result in a large number of requests waiting in the queue until the SLO is violated. The figure on the right shows the breakdown of the end-to-end latency. We can see that in addition to reduce cold start overhead, StreamBox also reduced the memory allocation and the communication overhead. And we have many other experiments. You can see the paper if you are interested in multi-tenant scenario or the ablation study and other system overhead. So, in summary, we propose a lightweight GPU runtime that is more suitable for serverless function. We argue that functions in an application do not require such strong isolation, and we utilize GPU strings to reduce redundant GPU runtimes. Moreover, we introduce a series of enhancements for strings based on the characteristic of serverless functions, including auto-scaling memory pool, intra-GPU communication, and the fine-grained PCIe sharing. Oh, that's all. Thank you. If you have any question, we can discuss together.